In this video, we're going to be looking at Equilibria, which is all about reversible reactions. You'll know a reaction is reversible when you see this instead of the normal arrow in the centre of the balanced equation. A reaction is said to be in equilibrium when the rate of the forward reaction equals the rate of reverse reaction. And at this point, we find that the concentration of reactants and products is constant. Not equal, but constant concentrations. When we have a reversible reaction, we can change things like concentration, pressure, temperature to change the position of the equilibrium, to shift it more towards the products or more towards the reactants, allowing us to control what's produced in a particular reaction. In terms of industry, chemical industry making products, we want to shift towards the product side. We say to shift the equilibrium to the right, and we'll be looking at ways to do that, and ways to do that to ensure profitability. With a reversible reaction here, A reacting to form B, and if we start with A, the reverse reaction can only begin once we've made some of B. Once we have B, we can start making A. Looking at this rate graph, you can see the rate of reaction for the forward reaction is high at the beginning when the concentration of reactants is high, and as they react, it starts to slow down. The reverse reaction, the rate is low to begin with because we didn't have any of the products to react, but as they are produced, the rate gradually increases. But of course, we've got this reversible reaction going on, so A is making B, B is reacting to form A, and eventually the rates of the forward and reverse reaction will be equal. So when the graphs level out, that's when the rates of the forward and the reverse reaction are equal. That's when we have our equilibrium. That's when equilibrium is reached. We can look at graphs at how the concentration of the reactants and products varies with time during the reaction. The reactants start high and then they get lower as they react to form product, and the product starts low and it gets higher as more is produced. Equilibrium is reached when the rates of the forward and the reverse reactions are equal, and at that point the concentrations will be constant. And that's when we see these graphs level out. And we'll call this a dynamic equilibrium because although the concentrations are constant, A is still reacting to form B, B is still reacting to form A. It is dynamic, the reaction continues. At equilibrium, we may find that the concentration of reactants is higher than that of the product. We say in this instance the equilibrium lies to the left. We can also have the situation where there's a higher concentration of products than reactants. In this case, the equilibrium lies to the right. And most of the time in industry, we are trying to push the equilibrium to the right, change the position, move it to the right to get more product. To shift the position of equilibrium, we've got to work with Le Chatelier's principle. And that says if a dynamic equilibrium is disturbed by changing conditions like concentration, temperature, pressure, the position of equilibrium moves to counteract that change. So it's a bit like a seesaw. If we push down on one side, the other side then pushes back to counteract what's happened. If we're looking at concentration, if we increase the concentration of reactants or decrease the concentration of products, the equilibrium will shift to the right towards the products. So with the Haber process, if we increase the concentration of our reactants here, we're going to increase the rate of the forward reaction, we'll shift the equilibrium to the right, and we'll end up with a higher yield of our product. Not all of the nitrogen and hydrogen will react in the Haber process, so what we find is that any unreacted is just recycled back round and into the vessel, and this helps keep the concentration of reactants high as well as adding more fresh reactants in as well. In the Haber process as well, the ammonia is distilled off as soon as it's made, so that's reducing the concentration of our products. So again, that's going to increase the rate of reaction of the forward reaction, shifting the equilibrium to the right, and we'll get more of our product again. A couple of sneaky things to be aware of. This rarely comes up, but it's worth knowing about. If we have silver nitrate will react with halogens, so chloride, bromide, iodide, and when it reacts with these ions, we get precipitates. The issue with that is that this is going to remove a reactant or product from the equation. So that's going to influence the equilibrium. So for example, in this equilibrium here, we've got a bromide ion here. If we add silver nitrate, we're going to form silver bromide, a precipitate which is going to come out of solution. So we're effectively getting rid of one of our products, decreasing the concentration of one of our products. That's going to cause our equilibrium to shift to the right. The second one to be aware of is hydrogen ions or acid or hydroxide ions, or it might just be like sodium hydroxide, potassium hydroxide. That will interact with acids and bases in an equation. So here we've got an equilibrium where hydrochloric acid is one of the products. If we add sodium hydroxide to this, the acid and the alkali will react together to give us salt and water. So effectively, we're reducing the concentration of one of our products, causing the equilibrium to shift to the right. So let's look at how a change in pressure will affect the position of equilibrium. The big thing to remember with pressure is it's all about moles of gas. State symbols are so important here. So for looking at the influence of change in pressure, we look at the total number of moles of gas in the reactants side and compare it to the total number of moles of gas on the product side. When we're doing this, we look at our coefficients in the balanced equation and we pay close attention to the state symbols. If we increase the pressure, the equilibrium will shift to the side with the fewest moles of gas. It tries to reduce the pressure. If we decrease the pressure, the equilibrium will shift to the side with the greater number of moles of gas to try and increase the pressure. The equilibrium shifts to counteract the change we've applied. So in terms of the Haber process, a high pressure will shift us to the product side to the right and will increase our yield of ammonia. In reality, high pressure equipment is very expensive, and so we settle for a medium pressure because a high pressure isn't cost effective. Looking at how temperature affects equilibrium, we really need to look at whether a reaction is exothermic or endothermic. And we remember that an exothermic reaction gives out heat, an endothermic reaction takes in heat, absorbs heat. The magnitude of the enthalpy change for a reaction, whether it's a forward or reverse reaction, is always the same, but one will be endothermic, the other will be exothermic. Here's a wee mnemonic to help you remember the effect of temperature on equilibrium. Intendo. Increase in temperature favours the endothermic reaction. So for temperature, if we add more heat, if we heat up our reaction, increasing the temperature, we will favour the endothermic reaction. Our equilibrium will shift to the cold side, to the endothermic side. If we cool things down, reducing the temperature, the equilibrium is going to shift to the hot side, to the exothermic side. So applying this to the Haber process, the forward reaction is exothermic, so that means it's giving out heat. Reverse reaction will then be endothermic. Heat is taken in, it will feel colder. In terms of getting the highest yield possible of ammonia, if we add more cold by cooling our reaction down, we're going to shift our equilibrium over to the right to the product side, giving us a high yield. What we've got to remember though is that temperature also affects rate. So if we cool it down, we will get a high yield of ammonia. However, it'll take a very long time for it to be produced. So if we're talking about industry and making a profit, keeping the reaction too cold is not profitable. So we generally do the reaction at a temperature of around 400 degrees Celsius to ensure a good enough yield at a sensible rate of reaction. Catalysts do not affect the position of equilibrium at all. If we think about what a catalyst does, it reduces or lowers the activation energy, but it's going to do this for both the forward and the reverse reaction. So it just means there's an increase in the rates of both the forward and the reverse reaction, but the equilibrium position doesn't change. It is, however, very useful in industry because we can have the reaction take place at in more economical conditions. So perhaps a lower temperature than we would have needed if we didn't use a catalyst. And the catalyst for the Haber process is iron, Hi. They're after each other in the alphabet. So Hi, Haber, iron. So a summary for the Haber process for getting a high yield of ammonia but keeping it profitable. Concentration, we want the equilibrium shifted to the right in all these instances. To do that for concentration, we recycle reactants and we remove the product as soon as it's made. This will increase the rate of the forward reaction, keeping our yield of product high. Pressure, we're thinking about moles of gas. So for pressure, there are 2 moles of gas at the product side, 4 moles of gas at the reactant side. So high pressure is going to shift us over to the low pressure side, fewer moles of gas, and that's going to give us a greater yield of product there. However, it's not cost effective to have too high a pressure because the equipment needed for high pressure experiments is too expensive. So a medium pressure is what's required in this reaction to keep it profitable. Temperature is another one where we compromise because forward reaction is exothermic, so if we cool things down we will shift the equilibrium over to the exothermic side, but if it's too cold the rate of reaction will be too slow to be profitable. So we have a medium temperature about 400 degrees Celsius, which ensures a sensible yield at a decent enough rate. Catalysts won't alter this position of equilibrium at all, but we can use the catalyst to speed up both the forward and reverse reaction rates, and it's used in industry a lot. Catalyst for the Haber process is iron. Things you should know about Equilibria now. A reaction is at equilibrium when the rate of the forward and the rate of the reverse reactions are equal, at which point there will be constant concentrations of both reactants and products. Not equal, but constant. With concentration, if we increase the concentration of reactants or decrease the concentration of products, the equilibrium will shift to the right. With pressure, it's all about moles of gas. So if the pressure increases, we're going to shift the equilibrium to the side with fewer moles of gas. If the pressure decreases, the equilibrium will shift to the side with greater moles of gas. With temperature, to shift the equilibrium to the exothermic side, we have to cool it down. To shift the equilibrium to the endothermic side, we have to heat the reaction up. So the catalyst, remember, it does not affect the position of equilibrium. It will increase the speed of the forward and reverse reactions and help equilibrium be achieved more quickly, but the position of equilibrium is not altered by the use of a catalyst.